For this example, I've prepared a function called serializedJSON. It accepts a value of type any, and it passes that value to the json.stringify method. Below, I'm defining a user object with two properties. I'm passing that to serializedJSON, and then I'm logging the JSON to the console. So before we move on, let's give this a quick run. I'm going to pull up my terminal, and first up, I'm going to compile this TypeScript project. And once that's done, I'm going to execute the resulting JavaScript file in Node. As we can see, the output of our program is the JSON serialized user object without any kind of indentation. Let's now say that we wanted to let the caller of the serializedJSON method control the formatting by specifying an indentation level. I'm going to create an object type called serializationOptions, and I'm going to add to that a property called formatting, and nested underneath that a property called indent. We can now add an options parameter using that type to our serializedJSON function. Within the function, let's pull out the indent value by saying options.formatting.indent, and let's pass that through to the json.stringify method. Finally, let's come down to the call side and let's pass some formatting options. Before we move on, I want to make sure that this works. So let's pull up the terminal and let's run our program again. And indeed, now we get a JSON object that's been indented with two spaces. Now let's say that we wanted to make this options object optional, so that the call side could also look like this. We can make the options parameter optional by appending a question mark to the parameter name. TypeScript is now giving us a type error, and it's telling us that this object is possibly undefined. This is a really valuable warning from the type system. The options parameter can hold the value undefined, so accessing options.formatting can blow up at runtime. Notice that in order to get this type error, you have to have enabled the strict nullchecks compiler option. In my tsconfig file, I've enabled the strict option, which enables strict nullchecks and a bunch of other strictness-related options. If for some reason you don't want to use the strict option, or you can't, the key option to enable is strict nullchecks. But I would encourage you to try and use strict whenever possible. So how do we work around this type error? Well, options can hold the value undefined. So before we access options.formatting, we have to check whether we actually have a truthy value. And if we don't, we can fall back to the value undefined. Let's also say that the formatting property itself is optional. So this means that at our call side, we can specify an empty object and we don't need to specify the formatting property. Now we get another type error, and this time, options.formatting is possibly undefined. So we need to do what we did before, and we need to first check whether options.formatting is a truthy value, and if it isn't, we want to fall back to the value undefined. You can already see that this is getting quite verbose. We've had to add two checks to make sure that options does not hold the value undefined and that options.formatting does not hold the value undefined. Instead of using these nested conditionals, we can use the optional chaining operator, which is written as a question mark and a dot. The optional chaining operator lets us safely descend into our object, all the way down to the indent property. If anywhere in this property chain the object that we want to descend into is null or undefined, we stop descending, and the optional chaining operator produces the value undefined. This is why TypeScript is inferring the union type number or undefined for our local variable. Now that we have the optional chaining operator in place, let's go ahead and let's give our program another run. We can see that we get the unformatted JSON object if we're not specifying the formatting object. And if we come in here and we explicitly set an indentation level, and we run this one more time, we can see that we get the formatted JSON object. The optional chaining operator comes in different forms, and the one we've seen right now is the one that's written dot. There's another form that we need when we don't have a simple identifier like we have here. If I were to rename this property to something like, say, indent level with a hyphen in it, we now get a syntax error in line 8. The quoted property syntax is valid in the type declaration, and it's valid in the object literal down here. but it's not valid in this property chain. We can still use optional chaining here if we use the index notation. I would generally recommend to stay away from property names like these because they're a little bit awkward to work with in JavaScript. But sometimes you might have a good reason to use a property name like that, or you might not have control over the property name at all. In these cases, you can use the index notation. The value between the brackets can be any arbitrary JavaScript expression, by the way. So if you were to work with arrays, you can use the syntax to access array indices, for example. Finally, there's a third version of the optional chaining syntax, and that's used for working with functions. To demonstrate the syntax, let me refactor our property to a method. And let's make sure this method is optional. We can now call this function in our optional property chain by stating the name and then the syntax dot and parentheses for calling the function. Now, this syntax might look a little bit funky to you initially, but you are going to get used to it. Just keep in mind that whenever you're using optional chaining, the operator always begins with a question mark and a dot, and it can be followed by square brackets or by parentheses. Notice that if we leave out the question mark dot, TypeScript gives us another type error, because it's saying that we cannot invoke an object which is possibly undefined. Let's give this one final run. And indeed, our code still works. Lastly, I would encourage you to have a look at the JavaScript code that TypeScript has generated for us. It's a great way to understand the optional chaining operators in detail. You can see exactly which null checks are being run, and you can also see that all properties are evaluated exactly once, and the result is stored in temporary variables. If I rename the temporary variables to _formatting and _getIndent, you can see that this code is looking similar to what we had initially before we started using optional chaining. In the previous lesson, we looked at the optional chaining operator and how to use it in TypeScript. In this lesson, I want to talk about the nullish coalescing operator, which is written as 2 question marks. It's oftentimes used in conjunction with optional chaining. But before we jump into the nullish coalescing operator, I want to motivate why it's useful. We can pass in the indentation level when we call the serialized JSON function. In this case, I'm passing the indentation level 2. If we don't specify the indent property, the default indentation level is 0, and we can verify this by running this program. In the output, we can see that the JSON is not indented at all, so the indentation level is 0. Now, let's say that we wanted the default indentation level to be 2 rather than 0. So if we don't pass an indent property, we should use the value 2. We can do this by using the logical OR operator and passing 2 as the right operand. If we run the program again, we can now see that the resulting JSON is indented with 2 spaces. Of course, we can also still specify a different indentation. So if I come back down here and I specify an indentation level of 4, and if I run this one more time, we can see that the output is indented with 4 spaces. Now, let's see what happens when I set the indent property to 0. We would expect the resulting JSON to not be indented at all. However, this is not what's happening. We still get an indentation level of 2, and this is because of how we're using the OR operator here. The logical OR operator has a left operand and a right operand. It evaluates to the right operand if, and only if, the left operand is falsy. If we have the expression null or 2, the resulting value is 2, because null is a falsy value, so the operator produces the right operand. Similarly, if we have the expression undefined or 2, we also get the value 2, because undefined is also a falsy value. However, we shouldn't forget that the number 0 is also considered a falsy value. So if we have the expression 0 or 2, the result is 2, because the left operand is a falsy value. This applies to other falsy values as well. For example, the values false, not a number, or the empty string. In all cases, the logical OR operator produces the right operand, because the left-hand side is falsy. This is where it gets a little bit tricky sometimes, if you're trying to mix nullable values with a logical OR operator. We want to provide a fallback value, but we only want to provide it for null and undefined, not for any other falsy values. This is where we should be using the nullish coalescing operator instead. The nullish coalescing operator is written as two question marks. It also takes two operands, and it produces the value on the right-hand side if the value on the left-hand side is null or undefined. Put differently, we only fall back to the right-hand side if we have a nullish value on the left-hand side. And nullish in this case means null or undefined. That's why it's called nullish coalescing. Now, here is where the operator comes in useful. If we have a falsy value on the left-hand side that is not null or undefined, we keep the left-hand side. So we can write 0, question mark, 2, and that expression will evaluate to the value 0. And this is exactly the behavior that we want in our serialized JSON function. For the sake of completeness, let's go through the other examples we've seen before. So we also tried the values false, not a number, and the empty string. And you can see that in all cases, even though these are falsy values, we keep the left-hand side when using the nullish coalescing operator. Alright, so let's jump back into our example and let's fix our code. Let's see if this actually works. And yep, we can see that we get the JSON serialized string with no indentation because we passed the value 0. Let's now set the indentation level to 4, and let's give this another run. And that's looking fine as well. And finally, if we don't specify any indentation level, we now use the fallback value of 2. You'll oftentimes see the nullish coalescing operator used in conjunction with the optional chaining operator. Optional chaining can produce the value undefined, and nullish coalescing is a great way to provide a fallback value. Be careful when using the logical OR operator. It might not have the behavior that you want. In a lot of cases, the nullish coalescing operator should be preferred over the logical OR operator. To know which one you should be using, ask yourself whether you want to provide a fallback value for falsy values or for nullish values only. Let's say we have a variable called value that is of type any. In TypeScript, all types are assignable to the any type. This means our value variable can hold arbitrary values. We can assign primitive values, such as booleans, numbers, or strings, but we can also assign more complex values, such as objects, arrays, or even functions. And of course, we can also assign the values null and undefined. When we are using the any type, we can essentially do anything. For example, we can access arbitrary properties, and we can call arbitrary methods. However, these operations can actually fail at runtime, depending on the value that we hold in our variable. Let me simplify this example a bit, and let's say that we want to take a string, uppercase it, and then print it to the console. So what we can do is we can assign this value to a variable called uppercase text, and then we want to say console.log uppercase text. Let's go ahead and open the terminal, and we're going to compile our TypeScript project, and then we're going to execute the compiled JavaScript file in Node. As you can see, we're getting the infamous error cannot read property of undefined. The problem with our code is that we're using the any type. When we're using any, we don't really get any protections from TypeScript. Also notice how the any type is spreading in our code. Value is of type any, and therefore the toUppercase method is also of type any. And therefore its return type is of type any, and therefore our uppercase text variable is of type any. We've pretty much lost useful type coverage in most of our code. Let's now look at a safer approach that uses the unknown type. Unknown is another universal supertype in TypeScript's type system, so this means that we can assign all types to unknown, just like we can assign all types to any. The big difference between any and unknown is that it's essentially flipping the default from allowing everything to allowing almost nothing. In our example, TypeScript is telling us that the value variable is of type unknown, so we cannot simply call the toUppercase method on it. First, we have to narrow the unknown type to something more specific. For example, the type string. One of the ways that we can do this kind of type narrowing is using the typeof operator. What we want to check is whether our value is actually a string before we try to use it as a string. Now, a bunch of things have happened. First of all, you can see that the type error went away. This is because out here, value is typed to be of type unknown, but within the if statement, we've narrowed our value variable to be of type string. So we can now call string methods on it, like for example, toUpperCase. Also note that now that we know that there's a toUpperCase method, we also know its return type, which is string. So uppercase text is now typed to be a string. Let's now go ahead and run our code again. As you can see, you see nothing. We no longer get an error, but we also don't get any output. This is expected though. We only want to log our uppercase string if we actually have a string. So if I go back in and I swap lines 2 and 3, value now actually contains a string. So if we rerun this one more time, now we actually get our uppercase string. Whenever you're unsure whether you should be using any or unknown, I would encourage you to bias towards unknown. It is the safer default, and TypeScript helps you put the correct checks in place rather than make assumptions about your values. Let me show you another example where we can use the unknown type. Here we have a range function. It takes from and to as parameters, and it returns the range of numbers in between those bounds. So if I run this code, we'll get the range from 0 to 5, excluding 5 itself. Now, if you're only using this function within your own TypeScript project, and you have good type coverage everywhere, you can stop right here, and you don't have to do what I'm about to show you. However, if you're exporting this function in, say, a JavaScript library published to NPM, there's a good chance you will have JavaScript consumers of this code, and some of them might not see your type annotations. So we might want to put some additional input validation in place. The unknown type can help us with that. Let's add some validation code to verify that our two parameters are actually two numbers. TypeScript can help us do this if we type our parameters as unknown instead of using the type number. The unknown type is our way of saying that we don't actually know the shape of the values we will be receiving. Within the body of our function, TypeScript is now giving us a bunch of type errors. And that's because we're using parameters of type unknown as if they were numbers, without checking that they actually are numbers. So let's put these checks in place. If either the from param or the to param is something else than a number, we want to throw an error and let the caller know that they are using the range function incorrectly. Now, TypeScript is really clever. It understands that from and to must be numbers. So if I hover over from in line 7, you can see that it has type number, and the same is true for to. If either parameter wasn't a number, we would have thrown an error in line 3 and we would have left the function. So if we actually make it past the if statement, from and to must be numbers. This is great. Our code is now more defensive than it was before. But we've also lost something in the process. If I hover over the range function call below, you can see that the from and to parameters now show up as unknown in the function signature, because those are the types that we have assigned. This is not great, because we want to communicate to our TypeScript callers that from and to are meant to be numbers. We can fix this by adding an overload signature to our function. I'm going to copy-paste the function signature, but instead of using the type unknown, we are going to use the type number. With this overload signature in place, callers of our function can now see that the from and to parameters are meant to be numbers. Within our range function, though, we are treating from and to as unknown values, and we first have to convince ourselves that we're in fact dealing with numbers. And if we accidentally forget to write one of these checks, TypeScript will tell us that we are working with an unknown value. This is especially helpful if we're trying to write defensive code. In the previous lesson, we worked with this range function. Here, we're passing the arguments 0 and 5 to the from and to parameters. Let's go ahead and compile this project, and let's execute the resulting JavaScript file in Node. We can see that we get the range from 0 to 5, excluding 5 itself. Now let's see what happens when I try to pass strings as arguments. For example, I could try to create the range of letters from A through F. Now TypeScript gives us a type error, and this is because both from and to are expected to be numbers. I'm going to use an asAny type assertion here to suppress these type errors. I'm just pretending that we're working with variables here which are typed as any. If I now run the program again, you can see that we get an error, because we're passing invalid arguments to the function. Alright, so we've convinced ourselves that our parameter checks are working correctly. Now I want to go ahead and I want to refactor this check into an assert function. Let's say that we want to have a function called assert. And our assert function is going to accept a condition, and it's going to accept a message. And if the condition is not met, this function is supposed to throw an error, and we're going to pass through our message. I'm going to use the assert function and verify that the from and to params are actually numbers. And I'm going to pass the same error message to the assert call. Now that we're using the assert function, we no longer need this if statement, so I'm going to remove it. Unfortunately, our code is no longer type correct, and TypeScript is giving us a bunch of type errors. This is because from and to are now inferred to be of type unknown. Unlike before, from and to are no longer narrowed to type number. This is because TypeScript doesn't understand that if this condition is false, our assert function will throw an error. We need to tell TypeScript explicitly that our assert function has that behavior, and we do that by adding what's called an assertion signature. This assertion signature says that whatever gets passed to the condition parameter must be true if our assert function returns regularly and doesn't throw an error. Notice that this is the behavior we've implemented here. If the condition isn't true, we throw an error. Otherwise, we implicitly return. TypeScript understands the implications that this behavior has on the control flow of the program. So if control flow actually makes it to line 16, it means this condition must have been true, because otherwise, assert would have thrown an error. This means that at this point, TypeScript can safely assume from and to be of type number. Instead of this combined assert call, we could have also written two separate assert calls. We can first assert that the from parameter is of type number, and then we can assert that the to parameter is of type number. The effect of these assert calls is the same as before. If control flow makes it past these assert calls, from and to can safely be assumed to be of type number. If I go ahead and run our code again, we can see that we get the correct error message, saying that from must be a number. Next up, I want to show you how we can write a more specialized assert function. So let's go ahead and delete the one we currently have, and let's say I want to write an assert function called assertIsNumber. This function is going to accept a value of type unknown, and it's going to accept a string. Within the body of the function, we're going to say that if the type of value is not a number, we're going to throw an error. We also need to add an assertion signature to our function, and this time we're going to assert that value is a number. This assertion signature says that unless our function throws an error, value can be narrowed to type number. With this assertion signature in place, we can go ahead, remove our two assert calls, and use our new function. With these checks in place, you can see that we no longer get any type errors. Let's run one final check to make sure we still get the right error. And indeed, we do. I want to show you another example in which we can use an assertion function. Here, we're trying to find a DOM element that matches the ID root. The document.getElementById method will return the element that has a matching ID. It will return the value null if no such element can be found. Therefore, our root variable is inferred to be of type HTML element or null. Let's assume we wanted to register an event listener for the click event. We could call root.addEventListener, and we would pass it the string click, as well as a callback function. As you can see, we're getting a type error. TypeScript is pointing out that our object is possibly null. And that's true. If the element can't be found, our root variable will hold the value null. We can deal with this type error in a bunch of different ways. One option we have is to use TypeScript's non-null assertion operator, which is written as a postfix exclamation mark after any expression. With this operator in place, our root variable is now inferred to be of type HTML element. Notice that null is no longer part of the type. However, this operator doesn't have any runtime manifestation, so when we compile our TypeScript file to JavaScript, it is completely erased. We don't actually get any protection at runtime. The root variable will still contain the value null, and if we try to call the addEventListener method on it, we will get the famous error cannot read property addEventListener of null. The safe way to deal with this null case is to add a null check. So we can say that if root is null, we want to throw an error, and as a descriptive error message, we should communicate that we couldn't find the DOM element we're looking for. With this null check in place, our type error goes away because if root is actually null, we throw an error in line 4 and never actually execute line 7. One more time, I want to refactor this check into an assertion function. I'll write a function called assert is nonnullish, and it's going to be a generic function with a single type parameter t. It's going to accept a value of type t, as well as an error message of type string. Within the body of the function, we're going to check whether value is either null or undefined. And if that's the case, we're going to throw an error. Lastly, we need to add an assertion signature. This time, we're going to assert that our value is of type nonnullable t. The nonnullable type is defined in one of the core type declaration files that ships with the TypeScript compiler. It is what's called a conditional type. We're going to look at conditional types in detail later in this course. For now, suffice it to say that the nonnullable type removes the types null and undefined from a given type. For example, if we have the type HTML element or null or undefined, we can remove those types null and undefined using nonnullable. All that's left is type HTML element. Alright, we can now use our assertion function instead of the if statement. We're going to call assert is nonnullish on our root variable, and we're going to pass the same error message, couldn't find DOM element root. Notice that we don't get any type errors. In line 10, root is inferred to be of type HTML element or null. But if control flow actually makes it past our assertion function call, the root variable is now narrowed to type HTML element. As you've seen, assertion functions can be really useful if we want to make assumptions about a certain value and get a runtime error if those assumptions aren't actually true. In this lesson, I want to compare and contrast different ways for working with class fields in TypeScript. Let's have a look at this counter class. It defines a field called value, and it exposes a method for incrementing the current value, as well as a getter for retrieving the current value. I'm going to create an instance of the counter class, and I'm also going to call the increment method a bunch of times. Now that we've incremented the counter a bunch of times, let's go ahead and log the current value to the console. I'm going to open the terminal, and first up, we're going to compile our project, and then I'm going to execute the index.js file in Node. And as you can see, we're getting the value 3 because we've incremented the counter 3 times. So far, so good. Now, note that the name of the value field begins with an underscore. This is a commonly used naming convention in JavaScript, which is meant to tell us that this property is meant to be private, and that we're not supposed to be changing it outside of the counter class. However, this really is just a naming convention. Even outside of the counter class, I can access the value field, and TypeScript even suggests it to me in the autocompletion list here. So if we wanted to assign a completely nonsensical value here, we could. So what can we do to prevent assignments like these? One thing we can do is to add TypeScript's private modifier to the field declaration. Now we're getting a type error in line 18, and TypeScript is telling us that the property value is private and that we can only access it from within the class counter. The TypeScript compiler will now warn us about inappropriate usages of the value prop, but it won't actually prevent inappropriate usages at runtime. The private modifier doesn't give us any actual protection. It's very easy for someone to actually get around this type error. For example, someone could simply add a tsignore comment in the line above, and now the type error goes away. Alternatively, you can also use the index notation to access the value field. And as you can see, TypeScript even suggests it here. This is kind of an escape hatch by the compiler. We can access a field with a private modifier outside of the class it is declared in. If I now run the program again, you can see that the private modifier didn't give us any protection at runtime. Alright, so let me summarize the private modifier. If we add TypeScript's private modifier to a class field, the compiler is going to give us a warning if we use that field outside of the class. It does not have any runtime impact, so the generated JavaScript code is going to behave exactly the same as if we hadn't added the private modifier. The most important thing to remember is that the private modifier does not give us any privacy at runtime. Now that we've seen TypeScript's private modifier, let's go ahead and let's refactor this class to use truly private class fields. All I need to do is rename the value field, and I'm going to make sure the name begins with a hash sign. This turns the value field into a truly private class field. Now the value field can no longer be accessed in any way from outside of the counter class. Note that, unlike the private modifier we've seen before, private class fields are not TypeScript-specific syntax. In fact, I can pull up the terminal and I can run the index.ts file in Node directly because we're not using any TypeScript-specific syntax. Let's see what happens when we try to use the value field outside of the counter class. If I try to modify the value field by saying counter.value equals -100, TypeScript now gives us an error, and it's telling us that the property value is not accessible outside of the class counter because it has a private identifier. Its name begins with a hash sign, so this makes it a truly private class field. If we now run the code again, we're finally getting an error at runtime. And it's saying that the private field value must be declared in an enclosing class. Notice that this is considered a syntax error. Writing counter.value outside of the defining class is not even considered valid syntax. The great thing about private class fields is that they're truly private. Outside of the class, not only can we not access the value of these fields, we do not even know about their existence. This gives us the freedom to rename and refactor our private class fields as much as we want, without having to worry that consumers of our class are depending on its internals, intentionally or unintentionally. For example, we might decide to rename the field to something like count. We can safely make that refactoring without having to worry about breaking a consumer of our class. Now, there is one caveat when you're using private class fields in TypeScript, and that is that the language level you're targeting needs to be ES 2015 or higher. So in your tsconfig file, you want to make sure that the target property is set to at least ES 2015. This is a requirement because the TypeScript compiler is emitting a weak map into the generated JavaScript to implement that notion of true privacy, and weak maps have only been supported as of ES 2015. Now, if you do need true privacy and you have to support an older JavaScript version, such as ES5, instead of using a class, you can use a closure. In our example, this could have looked as follows. We could have written a function called createCounter, and within that function, we could have defined a local variable called value. From within that function, we would return an object with an increment method, which would increment our value variable, and the getter we defined before, which will simply return the value of the variable. Lastly, instead of calling newCounter, we would now call createCounter. Note that this approach is still giving us the same benefits of true privacy. The local variable value is inaccessible from outside of the createCounter function. The only way we can modify this variable is using the increment method, and we can only do so in a controlled way. Let's run one final check to make sure that this is working, and that's looking all right. In this lesson, I want to talk about strict property initialization in TypeScript. I've written this simple user class which defines a username property. Let's go ahead and let's create an instance of the user class, and let's also set a username. Now that that's done, let's read the username, let's make sure it's lowercase, and let's print it to the console. Let's quickly go ahead and run this. And that is looking fine. Now let's see what happens if we don't call the setUsername method. If I go ahead and run the program again, we can see that we get a type error. And this is because we're trying to call the toLowercase method on the value undefined. So how come we didn't get a type error here? Let's head over to our tsconfig file and have a look at our compiler configuration. We can see that we have enabled the strict nullchecks compiler option, so we would have expected TypeScript to give us a type error here, right? Well, it turns out we need to enable another compiler option to get a type error here, and that option is called strict property initialization, and we want to set that to true. Whenever we enable the strict property initialization option, we also need to enable the strict nullchecks option. The TypeScript compiler has a bunch of options related to stricter type checking, and whenever possible, I would encourage you to enable all of them in your project. The easiest way to do that is to set the strict option to true. That will enable a bunch of compiler options related to stricter type checking, including strict property initialization. If we head back to our index.ts file, you can see that we now get a type error. TypeScript is telling us that the property username has no initializer, and that it is not definitely assigned in the constructor. We're essentially working with an uninitialized property, which is why we get the value undefined. One way to work around this type error is to add the type undefined to our property declaration. Now we've solved the type error in line 2, but now we get another type error in line 12, and this is because we're working with a possibly undefined value. This is the behavior that we want. TypeScript is warning us that this operation might fail at runtime. We can safely work with a username property by using optional chaining, and we can even provide a fallback value using the nullish coalescing operator. If we now go ahead and run our program again, we can see that we get the fallback value when the username is missing. And if we actually set a username, and we run this again, we can see our username. Another approach we could take would be to initialize our username property with our fallback value. That way, we always have a string value even if we don't call setUsername. And this means that we can remove the undefined type from our property. In fact, we can remove the type annotation altogether because TypeScript can infer from the initial value that this must be a string property. Now, we can also remove our null handling in line 12, because we no longer have to cater for undefined values. Now, this approach works, but I feel like it's not the most idiomatic one. If username is actually a mandatory property of our user class, we should accept a username parameter in the constructor. So let's go ahead and let's add a constructor here, and it's going to accept the username as a parameter, and within the constructor, we're going to assign our username. Now we can also remove the initializer here, and we can say that this is a string property. Now we're getting a type error in line 13, and this is because we're not providing an argument for the username parameter. So let's pass the username to the constructor. TypeScript can figure out that after the constructor has run, the username property has definitely been assigned. However, if there is any path in the constructor that doesn't assign the username property, TypeScript gives us the type error again, and it's telling us that the username property has not definitely been assigned in the constructor. Now, for this analysis to work, you have to assign the properties directly within the constructor. TypeScript does not track property assignments across method calls, because that could get arbitrarily complex and expensive. If we were to call the setUsername method instead of directly assigning the property, we would be back with our type error, because TypeScript's analyses cannot detect that we have definitely assigned the username property. There is a way to tell TypeScript that we will definitely assign this property, even if TypeScript cannot detect that itself, and that is to use what's called a definite assignment assertion. It's written as an exclamation mark after the property name. TypeScript will now trust us that we will initialize the username property in all cases. Definite assignment assertions can be useful if you're initializing some of your properties in an initialize method. For example, we could have a method called initialize. perhaps even a private method, that will initialize our properties, in this case the username property. That said, I want to caution you a little bit against definite assignment assertions. If we don't actually assign a property in our initialize method, and we execute our program again, we will run into the same error we've had before, and TypeScript did not warn us about it. TypeScript trusted us when we said that we were going to initialize all of our properties. The safest way to work with properties is to initialize all of them in the constructor, so that's what I would recommend. If you initialize all of your properties in the constructor, you don't need a definite assignment assertion, and TypeScript can give you more type safety. Here we have a generic function called intersperse that defines a single type parameter t. It accepts an array of values, of type t-array, and it accepts a separator value of type t. This function returns a new array of type t that has the separator value interspersed between all of the array elements. So let's say we've defined an array of values a, b, and c. We're going to pass this array to the interspersed function, and we're going to sprinkle in the value x. What we're going to get back is a new array, which we're going to store in the variable values with separators. Now let's go ahead and log both arrays to the console. I'm going to open the terminal, compile our TypeScript project, and execute the resulting JavaScript file in Node. And as you can see, here we have the two arrays as expected. Note that our values variable is inferred to be of type string array, and that's because we've initialized the variable with an array of strings. Alternatively, we could have also explicitly typed our variable as a string array. Now let's see what happens when we make our array type read-only. If you have a read-only array type, TypeScript will give you a type error if you're trying to mutate the array. For example, we cannot push additional values into the array, and we also cannot remove existing values from the array. We get a type error saying that property push does not exist and property pop does not exist on type read-only string array. If we had been using a mutable array type here, both operations would have been type correct. We also get a type error in line 13 saying that the argument of type read-only string array is not assignable to a parameter of type string array, and that's because the parameter of type string array is considered to be mutable. We can solve this issue by changing the type of our array parameter to read-only t-array. We're not mutating the array within our intersperse function, so working with a read-only array type is enough for us. Notice that even if the parameter is a read-only array, we can still pass a mutable array to it. It just means that within the function, we cannot access mutating methods on the array. There is another syntax for defining a read-only array type, and that is using the read-only array type and passing it a generic type argument. They're interchangeable, so you can use whichever version you prefer. Now, I prefer the version using the read-only keyword just because it looks a little bit closer to how we would usually be declaring an array type using the square bracket notation. Similar to how TypeScript supports read-only array types, it also supports read-only tuple types. Here we have a generic function called swap. It defines two type parameters t and u, and it accepts a single tuple with two elements of type t and u. The return value is a new tuple in which we've swapped the first and second element. Let's go ahead and use our swap function. Let's say that we have a key value pair where the key is the number 1 and the value is the string 1. Now we want to turn that into a value key pair where we swap the two values. So we're going to call swap and pass it our key value pair. As you can see, we're getting a type error. TypeScript is saying that the argument of type string or number array is not assignable to parameter of type string or number tuple. This is because we've made a mistake here. If we hover over key value pair, you can see that TypeScript has inferred key value pair to be of type array of string or number, but this is not what we wanted. What we wanted was a tuple type, where the first element is a number and the second element is a string. Now our code type checks correctly. And if we hover over value key pair, we can see that we get a tuple in reverse, where now the first element is a string and the second one is a number. Alright, so now that our code is type checking, let's verify that it actually works. So I'm going to log our key value pair to the console, as well as our value key pair. Let's compile the project again and run the file. And as we can see, we get two tuples, our original tuple and the swapped one. So just like before, let's go ahead and let's use a read-only tuple type here. And just like before, TypeScript is giving us a type error. And again, it's telling us that our read-only tuple type is not assignable to the parameter tuple type, because the parameter tuple type is considered to be mutable. We can fix our code by going up here again and making our function accept a read-only tuple. And now, as you can see, all the type errors go away. If you're writing a function that accepts arrays or tuples, consider adding the read-only modifier to these array and tuple types. That way, your function can be used with mutable arrays and tuples, as well as read-only arrays and tuples. Here I have defined the origin point, which has x and y coordinates of 0. I've chosen an all uppercase name to signal that we do not want to be changing these values, so origin is meant to be a constant. However, TypeScript will happily let us mutate the properties of this object. And this is because the object is inferred to have two mutable properties, x and y, both of type number. What we actually want is two read-only properties. However, we cannot just go in here and add the read-only modifier, because this would not be valid syntax. Instead, we have to add a type annotation to the object. And within this object type annotation, we can now declare two read-only properties for our point. With this type annotation in place, TypeScript is now telling us that we cannot assign to x because it is now a read-only property. So far, so good, but if you look at our code, you can see that most of it is now our type annotation. It is quite verbose. There is an alternative way of typing this object here, and that is using a const assertion. So let me go ahead and delete this type annotation and add the type assertion as const. This const assertion does a few things for us. First of all, when we use it on an object literal, like we are doing here, TypeScript is inferring every property to be read-only. Because of that, we still get the same error saying that we cannot assign to x because it is a read-only property. Also notice that both of our properties do not have the type number. Both x and y have the numeric literal type 0, and this means that they can only contain the value 0, rather than any arbitrary number. When we use a const assertion, TypeScript will not widen our literal types. And what this means is that we are not going from the value 0 to the type number. Instead, TypeScript is inferring the most specific type possible. And in this case, that is the numeric literal type 0 for both of our properties. Now, keep in mind that const assertions are a feature of TypeScript's type system. They don't have any runtime manifestation, so at runtime, we will still be able to change the properties of our object. If we wanted the entire object to be frozen and immutable, we could call the object.freeze method on it. And now the assignment in line 6 to our x property would fail at runtime. We can also use const assertions with array literals. In this example, I've modeled our point to be a 2-tuple. However, TypeScript is inferring the type number array, which is not what we want here. We would want TypeScript to treat this as a tuple of 2 numbers. Ideally, we would even want this to be a read-only tuple of 2 numbers. As you can see, our type annotation is getting quite verbose already, so instead of adding this type annotation, we can use a const assertion again. With this const assertion in place, TypeScript will infer a read-only tuple type. And once again, it's going to infer the numeric literal type 0, rather than widening that to the type number. If we now try to modify one of the tuple elements, TypeScript will give us a type error, and that's because we have a read-only tuple, so we cannot just change one of its elements. If you think back to the previous lesson about read-only array and tuple types, const assertions would have been really useful here. Remember that we added a tuple type annotation here, so that we would get a tuple type and not an array type. Instead of adding this type annotation, we could have used a const assertion instead. Once we add the const assertion, TypeScript will infer a read-only tuple type with 2 elements. And once more, TypeScript is going to infer the most specific types possible. So instead of inferring type number and type string, we now have the numeric literal type 1 and the string literal type 1. Const assertions are particularly helpful if you have slightly more complex literal expressions. In this case, I've declared an array of tuples, but what TypeScript sees is an array of arrays that contain either strings or numbers. That type is not really as specific as we would like, so what we can do is add a const assertion. Now, TypeScript is going to infer a much more specific type. Granted, the type is quite verbose, but it is precisely describing our digit names. In this example, I want to show you how we can use const assertions with enum-style objects. My fetch.json function here accepts the HTTP method as a parameter, and down here in line 6, I am passing in the string get. Let's go ahead and refactor these HTTP methods into an enum-style object. I'm going to declare a variable called HTTP request method. Let's define a get property, and let's also define a post property. We can now replace the string literal get in our fetch.json call by HTTP request method.get. However, TypeScript is now giving us a type error, and it's saying that the argument of type string is not assignable to the parameter of either string literal type get or string literal type post. We are getting this error because both the get and the post property are inferred to be of type string. They are not inferred to be the specific strings get and post. We can add a type annotation to our enum-style object, and we can tell TypeScript that we want the get property to have the string literal type get, and the post property to have the string literal type post. And while we're at it, we might as well make both properties read-only. Our code now type checks correctly, and this is because the properties of our enum-style object now have the correct string literal types. Now, if you look at the declaration of our enum-style object, you can see that we are repeating every HTTP method 4 times, and also our type annotation is getting more verbose. Instead of using this type annotation, we can add a const assertion. With the const assertion, TypeScript will now infer the type that we just annotated ourselves. Now there is one more refactoring I want to make, and that is to derive this union type from the values of our enum-style object. To make that a bit easier, I'm going to write a helper type called valuesOf, and it's going to accept a generic type parameter t. What this type does is access the types of all properties in this object. I'm using the keyof operator here and what is called an indexed access type. Next, I'm going to create a type called HTTP request method type, and it's going to use the values of helper type to extract all the property values from the HTTP request method enum. Note that HTTP request method is a value, not a type, so we have to use the typeof operator here. If I hover over the HTTP request method type, we can see that TypeScript has correctly extracted the string literal types get and post. This means I can now replace this union type by our HTTP request method type. Now, in this entire example, we've been using standard JavaScript syntax as well as TypeScript syntax. We have not been using TypeScript enums. JavaScript itself does not have enums, so we typically write these enum-style objects. In TypeScript, however, we could have also implemented HTTP request method as a TypeScript enum. The syntax for that is to say enum and then the name, and within the enum we would have two members called get and post. Lastly, since enums are both a value and a type, we can refer to the enum name directly here. Really, it's up to you whether you want to be using a TypeScript enum or an enum-style object. Some people like to avoid TypeScript enums because they are not currently a standard JavaScript feature. I find that this example is a little bit more readable using a TypeScript enum, but honestly, we could have also stuck with the enum-style object. Let's have a look at conditional types in TypeScript. Conditional types are definitely an advanced feature of the type system, but a very powerful one. A conditional type lets us express a type relationship test, And depending on the outcome of that relationship test, it produces one of two possible types. A conditional type always has the following structure. It first checks whether some type t extends some type u, and if that's the case, the resulting type is x, and otherwise, the resulting type is y. Notice that this syntax mirrors conditional expressions in JavaScript, or sometimes referred to as the ternary operator. We have some condition, and if that condition is truthy, we produce some value, and otherwise, we produce another value. Alright, so with the theory out of the way, let's jump in and let's write our first conditional type. I want to write a type called nonnullish of t. And what this type is supposed to do is remove the types null and undefined from the given type t. I'm going to start with the type relationship test. So I'm going to say if t extends the type null or undefined, then we want to produce type never. Otherwise, we want to produce type t. Now, this type might look a little bit cryptic, so let's take a look at the different parts. First, we're declaring a type alias called nonnullish, and we're accepting a single type parameter called t. Then we have the type relationship test. Here we're saying that if t is assignable to type null or undefined, we want the resulting type to be never. And if that's not the case, we want the resulting type to be t. I'm going to walk you through an example in a minute, and then you're going to see why we've chosen the never type here. But before I'm going to do that, let's have a look at some examples of this type in action. Here, I have 5 applications of the nonnullish type. In the first example, we're applying the nonnullish type to type string, and the resulting type is string. That's because if we remove the types null and undefined from the type string, we're still left with a type string. In example B, we're removing the types null and undefined from the union types string or null, and the resulting type is string. The same is true for type C. We have the union types string or null or undefined, but when we remove null and undefined, well, we're just left with string. Now, in example D, the resulting type is never, and that's because we're removing the types null and undefined from the type null, so the only thing we're left with is never. And in the last example, we also get type never, because we have the union type null or undefined here, and we're removing both null and undefined, so what we're left with is type never. It turns out that this helper type is useful in a lot of TypeScript applications. This is why it's actually defined in one of the core type declaration files that ships with the TypeScript compiler, so we don't have to define it ourselves. So I'm going to go in here, and instead of using nonnullish, we're going to use nonnullable everywhere. If I jump to the definition of the nonnullable type, you can see that it's defined in exactly the same way in the lib.es5.d.ts file. Let's have a look at a practical example now. Let's assume that we have a type called email recipient, and it's defined as either a string, or an array of strings, or the types null or undefined. I'm also going to create another type called nonnullable email recipient, and this type evaluates to the union type string or string array. This is because when we remove null and undefined from this union type here, we're left with the type string or string array. Now I want to walk you through how we can resolve this type step by step. And the first thing I'm going to do is inline our email recipient type here. When we apply the nonnullable type to a union of types, that's equivalent to applying the nonnullable type to every type individually. So what we get here is still a union type with 4 constituent types. But now we're applying the nonnullable type to all these individual types. So we have nonnullable of type string, or nonnullable of type string array, or nonnullable of type null, or nonnullable of type undefined. Next up, I'm going to inline the definition of the nonnullable type. So if I hover over that and I copy the definition, we can come back in here and we can start inlining. If we apply the nonnullable type to the type string, what we get is this conditional type. And we can do the same to the other types as well. Now we can actually evaluate our conditional types, starting with the first one. the type string is not assignable to the union type null or undefined. So what we're left with here is the type string. The same is true for the next line. The type string array is not assignable to the type null or undefined. So again, we're left with the type string array. The type null, however, is assignable to the type null or undefined. So in this case, we're producing the type never. And similarly, the type undefined is also assignable to the union type null or undefined. So again, we produce never. Lastly, if we have the type never in a union type, we can simply remove that. And this is because never represents values that can never occur. So we can remove that from a union type. And here we go. We're left with a union type string or string array, which we've seen in the beginning. Conditional types are often used to implement various helper types. For example, here we have a type called returntypeof that accepts a generic type parameter t, and if that type t is a function type, it extracts the return type. I've implemented this type using the infer keyword. So here we have our type relationship test. We're checking whether the generic type t is assignable to this function type. And this function type says that we have a function that takes an arbitrary number of arguments of arbitrary types and that returns a type which we can refer to as u. If that type relationship test is true, and our type t is actually assignable to this function type, which has the inferred return type u, we produce the return type u. Otherwise, we produce the type any. Note that we can only refer to the inferred type u in the true branch of the conditional type. If I try to refer to u here, TypeScript gives me a type error, and it's saying that it cannot find the name u. This makes sense, because if the type t is not actually assignable to this function type, there's no way for TypeScript to infer this type u. Let's have a look at a few examples. In example A, we're determining the return type of this function type, which does not accept any parameters and which returns a string. So unsurprisingly, we get the return type string. In example B, we're determining the return type of the math.random method, and that is indeed a number. And in example C, we're doing the same thing with the array.isArray method, which returns a boolean, so the inferred return type here is boolean. Now, our return type of helper type is currently a little bit too permissive. We currently can pass a type to it that is not actually a function type, for example the type string. This is because we haven't added any constraints to our generic type parameter t up here. So what we can do is we can add a type constraint, and we can say that our type parameter t must itself be a function type. So it must be assignable to a function type with an arbitrary parameter list and an arbitrary return value. Now we get a type error in line 8 because the type string does not satisfy this function constraint. Now you'll find that a lot of developers are using single letter names for their generic type parameters. But we don't have to do that. We can actually pick descriptive names here. For example, we could rename the type t to t function. And similarly, we can rename the type u to something like t return type. Maybe this type is a little bit more readable this way. Finally, I want to point out that the return type helper type is built into the core type declaration files shipping with the TypeScript compiler. So we don't actually have to define it ourselves, we can simply use the built-in return type helper type. And if we jump to the definition, you can see that it's defined exactly the same way as we've just defined it. While you're in here, I would encourage you to have a look at some of the other built-in conditional types. You can learn a lot about TypeScript's type system just by having a look at the built-in type declarations. It can be a little bit overwhelming at times, but you'll learn so much about TypeScript syntax and the capabilities of the type system. Let's say that we wanted to statically type CSS declarations in TypeScript. Here, we have a union type of the two string literal types margin block and margin inline. We could have also written this type declaration using TypeScript's template literal types. First, let's extract a type called dimension that's equal to the string literal type block or the string literal type inline. Now, we can rewrite this union type using a template literal type. To define a template literal type, we use the same backtick syntax that we use for template literals in JavaScript. We want our template literal type to begin with the prefix margin hyphen. And then we want to interpolate our dimension union type. And just like with the backtick syntax, we're using the same syntax for interpolating values, the $sign followed by curly braces. Dimension is a union type, so TypeScript will expand our template literal type into a union of all the strings that we can represent this way. If I hover over the type name, you can see that the generated string literal types are margin block and margin inline. Now, template literal types let us interpolate more than one literal type. So let's assume we also had to find a type called direction. That could either be the string literal type start or the string literal type end. If I go back into our template literal type, we can now also interpolate the direction type. Our margin property type now represents 4 string literals, the combinations of all values of dimension and direction. So we get margin block start and margin block end, as well as margin inline start and margin inline end. Alright, let's keep going with this example for a bit and let's see how far we can take it. Let's say that we also wanted to define a margin value type that would be equal to a number. So we're simply creating a type alias here. Using our margin property and margin value types, we can now create a margin declaration type. For the sake of simplicity, I've decided to go with a tuple type here, but you could have also modeled this as an object type. Let's go ahead and actually create a margin value. So I'm going to say const margin, and I'm going to add a type annotation here, equals, and as I type the double quotes, you can see that TypeScript gives us auto-completion suggestions. So for example, I can pick margin block start, and we can set a margin block start value of 16. Note that all of this is fully type checked. So if we make a typo here, TypeScript gives us a type error, and it's saying that our incorrectly spelled property name is not assignable to this union type. Notice that we're using a number here. Let's say we wanted to make this a string value with the pixel suffix here. We can statically type this using another template literal type. This time though, we'll be interpolating the type number. If I come back down to our margin value, you can see that we now get a type error if we use a unit other than pixel, or if we leave out the unit entirely. Let's now say that we wanted to add support for other units, for example, the viewport height unit. In our template literal type, we can add another union type. So in here, we can say that we either accept the unit pixels, or the unit viewport height, or the unit viewport width. And if this union type gets too unwieldy, we can always extract it into a named type, for example, margin unit. Before we wrap up this example, I want to simplify the code a little bit. Our margin property type is fully known ahead of time. There's no need for us to use a template literal type to put it together dynamically, so we can simplify this code and write out the entire union type ourselves. I want to show you how we can use template literal types in a more complex example. I've prepared a function called createGetterObject, and what that function does is it accepts an object, like this user object here, and it returns a new object in which all the properties have been replaced by getter functions. If I write all of this to the console, we can see what that looks like. Let's call the getName method, and let's also call the getTwitter method. You can see that the resulting object has 2 methods, getName and getTwitter, and when we call those, we get back the original values. Let's try and statically describe this behavior in TypeScript. I'm going to create an object type called propGetters with a single type parameter tObject. We're also going to add a generic type parameter to our function, and we're going to update the types of our parameters, as well as the return type. Now, we're getting a type error in line 6, and this is because our generic type parameter is currently unconstrained. It could actually be any type we can think of, so we cannot safely access into it like this. So what we'll need to do is to add a constraint to our generic type parameter. We only want this function to be used with object types, and those object types have to have string keys, but they can have arbitrary values. Now, the first thing we want to do in our prop_getters type is to make it a mapped type. A mapped type lets us create a new object type from an existing object type. And this is exactly what we need here. We want to map over all keys in the object type, and we want the resulting type to be a function type that returns the type of that property. There's a lot going on in this line, so let's have a detailed look before we continue. We're using the keyof operator here to get all keys of this object type. The keyof operator produces a union type of all the property names, and then we map all of these property names to a function type. The property name is represented by the t_key type, so we can refer to it by using t_key. Here, we're writing out the function type. It doesn't take any parameters, and the return value is a lookup type, also known as an indexed access type. Essentially, we're looking up the type of the property named t_key in t_object. So for example, for a name property in this object, the resulting type would be a string. If I go down to line 20 and I hit the dot here, you can see that TypeScript suggests two properties in the autocompletion list, and both of them are functions returning a string. Now, notice that the names of the properties aren't quite right yet. The names are currently name and Twitter, but we want them to be getName and getTwitter. This is where we can use a template literal type. We can come back into our map type and we can add a key remapping, and we're going to remap the keys onto a template literal type. We want our property keys to be the string get, followed by the name of the key. TypeScript isn't quite happy with us yet, and it's giving us a big pyramid of an error message. The problem is that our keys are not necessarily literal types, but we need them to be literal types so that we can interpolate them into our template literal type. Given that we only care about string properties in this example, we can add an intersection type here, and we can say that we want the intersection of all keys in the type string. This way, we'll only keep those property keys that are strings, and the type error goes away. Alright, so now that we have the key remapping in place, let's go down to line 20 and let's see how far we got. You can see that we now get two properties, getName and getTwitter. However, notice that the capitalization isn't quite right yet. This is because we're interpolating the name of the key exactly as it is. What we want to do instead is to capitalize the key name. The capitalize helper type takes a string literal type and it uppercases the first character. Let's have a look at its definition. You can see that it's defined using the intrinsic keyword. The intrinsic keyword is reserved for a special set of helper types that are implemented in the TypeScript compiler itself. We couldn't write this capitalized type ourselves. There are a bunch of other types that are defined the same way. So we also have types for uppercasing strings, lowercasing strings, and uncapitalizing strings. Notice that all the type errors have gone away now. Let's go down to line 20 one more time. Let's hit the dot. And now you can see in the autocompletion list that we have our properties getName and getTwitter, and both of them have the expected function types. If we now add another property to our user type, for example, a numeric ID, we can come back down here and we can call user.getID, and you can see that the property has the expected type, a function returning a number. Before we wrap up, there's one final tweak that I want to make, and that is to add a type constraint to the t_object_type parameter. We want to make sure that people use the prop_getters type correctly, so let's add the same type constraint we've added above, and let's require the object types to have string keys and arbitrary values. As you've seen, template literal types can be really powerful and flexible. They let you statically type even highly dynamic code, and you can get even more advanced than what I've shown you here. I would encourage you to take some time and play around with all of these advanced types to see just how far you can push the type system.